In this video, we'll be introducing the concept of the mole, the chemist's mole, not the biological mole, and how we use it to determine numbers of atoms within 6 grams of CO2 or the number of aluminum atoms in 6.45 grams of aluminum. So we'll be able to use the mole to go from macro amounts like grams to micro amounts in moles or numbers of atoms. So it's a connecting point. It's a bridge between those two worlds that a chemist lives in. What he can see in his hands, what he pictures in his mind. So it's pretty important. Don't be too intimidated by the word mole. It's just simply an amount in terms of numbers. It's a very large amount, 6.02 times 10 to the 23rd of anything is a mole. 6.02 times 10 to the 23rd, and it's known to be a little bit more now precise, maybe like 5 places past the decimal point, but it's that amount of anything. We can have a ream of paper, which is like 500, a dozen eggs to a pair, but this is just a chemist sort of grouping. Very large amount of atoms, because in order to see them, you need to have a grouping that's really big. So that's kind of the idea of a mole. It's just an amount that's a very large amount, and we bundle it together and call it a mole. Where did it come from, and how do we kind of define it? Well, Avogadro, I guess, was the chemist who came up with it. And we now consider it in terms of its number to be that number that represents the same number of particles in exactly 12 grams of not just any carbon, but the isotope carbon-12. And we're learning it to be, we're getting it more and more precise. So that's how we define it. It's the exact number of carbon-12 atoms in exactly 12 grams of that carbon-12. And to get a sense for how large 6.02 times 10 to the 23rd is, it's more than the age of the Earth in seconds. And remember, the age of the Earth is 4.5 billion years old after Theia hits, and it cools way past population of the Earth, even past the amount of water in the world's oceans and liters. It's 2 places past that. And again, why so large? Because the number of atoms in any pile that we're trying to see has to be near that level. Maybe not exactly that number, but 1/1000th of that or 1/100th of that to even see it. All right, so we know it's a very large amount of anything. So again, don't forget, kind of be in the chemistry club if you can just spout off the term or the amount. What's a mole? 6.02 times 10 to the 23rd of anything. So we can say, using that number, that the atomic mass, or sometimes you'll see this referred to as the molar mass, the mass of one mole of that atom, or in terms of molar mass, that compound. So again, we can say mole of anything. So if we're saying atomic mass, we'll say atom. But if we're saying molar mass, we might say compound or molecule, something that has more than one atom. We can convert number of grams to number of moles. When we are going through this bridge, we can take one conversion from grams to moles, but we can also take it further and say, I can convert the number of moles to number of atoms. Again, we said it's the bridge between the macro and the micro, and you can't really talk about the number of atoms as something you see because it's just impossible, but we can use this term moles to get us to that point. And then we can put all A and B together and say, hey, what if I have the grams of something like dry ice, CO2, I can convert that through the molar mass conversion to the number of atoms, let's say, of oxygen and CO2. That's sort of a combination of these two. So it's really nice that you've learned dimensional analysis, the conversion train, because we use it a lot in this chapter. So here's an example. I have a mass of magnesium in the lab. Looks kind of weird, like a little fish there. Like a little fish here. It's got a little mouth. So we have that piece, and we want to know maybe what's the number of magnesium atoms roughly in that piece of magnesium metal. Well, I can weigh it. That's the first thing I have to do, is get some capturing of its amount in weight. So it's 5.657 grams. There's 4 sig figs. And what I can do then is I can take and convert that to the number of moles. Now we can do that using what you learned as changing the ratio. Here's one way, again, you can use conversions, and there'll have to be some points where you use dimensional analysis, but this is not one of them. You can use that changing the ratio approach. So we know from a periodic table that 1 mole of magnesium is equal to 24.31 grams. We've talked a little bit about how that weight that's in the periodic table for magnesium, when you find Mg on the periodic table, there'll be a measurement that's underneath. It says 24.31 or something close to that. That can be in AMUs if we're talking about the atom of magnesium, or we've talked in class a little bit about how that AMU can also be just representing grams of 1 mole of magnesium. We're going to focus on the latter. We're always going to see now the periodic table as, hey, when I'm looking at the periodic table, I want to think I've got 1 mole and it's equal to 24.31 grams. 1 mole, large amount, equal to 24.31 grams. But I don't have 24.31 grams of this magnesium. I have 5.657. So that's okay. We can set the ratio as, A to B is equal to C over D. Apples to oranges, moles to grams, moles to grams. And we can find that X amount of magnesium that I have in moles for this piece that I found in the lab, just by using a known ratio and having one of the numbers, the weight. We can solve for the top and isolate X. And if you do that, you'll end up, if you do cross multiplication, you'll end up with 0.2327 moles of magnesium. We could stop there if we wanted to, if that's, let me put that up a little bit higher. We could stop there if we wanted to, but we could also, if we wanted to, go past moles and know the number of atoms of magnesium. We could take that number, and I'm showing this in sort of a dimensional analysis approach, we could take that number and go one step further, dividing it by mole term and knowing that we have to multiply by 6.02 times 10 to the 23rd. Now, one thing I want to just recommend real quickly that you can do just to get a quick number, when you're using scientific notation, you can leave the 10 to the 23rd out of the calculation and then put it back on at the end. So let's go ahead and show that real quick. I can take the 0.237, 0.32327, and I'm going to multiply it by the 6.02. I'm just going to leave it at that. I'm not going to multiply by the 10 to the 23rd or use it in scientific notation. If I just do this times this and leave this out, I get 1.40, and we'll leave it as 1.401 because that's what we get. So if I do this, and I'm going to put it right here, 1.401, I can just bring this back in after I'm done multiplying these two. On the top has to be multiplying something on the top because we have this on the bottom. This cancels. And I would have 1.401 times 10 to the 23rd, because I'm just going to bring that back in, the 10 to the 23rd. You can do that sometimes with simple calculations involving scientific notations. Just leave that off for now, do all the work with the number out front, and then bring it back in. Now, from this point on, I will not be doing any more calculations involving dimensional analysis, but I'll be setting up the train, and then we'll be doing those calculations in class to check our train. So for example, we're just going to put the train together, and then we will let you come up with the math, the number, the final number. But setting up those trains is really, really important. So to do that, what I have is a little guide on the right here. We're always going to remember that we have to kind of think of it in sort of a pathway. We can go from grams to moles to atoms as our pathway, or we can go atoms to moles to grams. It just depends on the question. So if we read the question, it says, calculate the number of moles of calcium contained in 15.84 grams of calcium. Stop. So what you have is they want to know this as a goal, and where you are is in grams. So you can look over here and say, well, you know what, I'm looking at my map, and I am right here. That's what it gave me. And they want me to go, so my goal is to get to moles. So it's just one step, grams to moles. So that means you're going to have one conversion factor. So you're going to set your 15.84 grams as your starting point. You're going to have one conversion factor. You don't know what it might be right now or whatever, but you know it's grams to moles, one step. And that's going to give me the number of what I want, moles of calcium. Well, this is grams of calcium. So what I have to do is look at the periodic table. And if I look at the periodic table, it tells me there's 40.078 grams, again, not AMUs, in 1 mole of calcium. So where does moles of calcium have to go in this conversion? It better go on top, because I want to end with the term mole, and I need to get rid of this gram amount. So 40.078 grams of calcium. So when you do the cancellation of units, you would indeed be left with the unit you want, moles. And so we can just take 15.84 and divide it by 40.078 to get our answer. But again, this is the point at which I'll stop. I really want my students to be able to build the dimensional analysis that we need to solve the problem. And we've done that. We have made the conversion. We'll train with just one conversion car, so it's not a lot. So that's our first example problem. We're going to do 3 more, and then we're going to leave the rest for class. Now, moving past atoms, we are needing to sometimes work with compounds. So compounds are different. Compounds are atoms together that are 2 different atoms. Remember, compound is any 2 or more atoms that are different that come together. So we're going to have water that has oxygen and 2 hydrogens. We can have an ionic compound that has sodium and chloride in a 1-to-1 ratio. That's an ionic compound. And to find their weight, we can just take and find where they are on the periodic table. So, for example, if I had some silver sulfide, we could find the silver and we could find the sulfur and the sulfur, and pull them together, just add them up. So we just do that. We sometimes go around the periodic table to find, let's say, carbon dioxide. I would find the carbon, and I would find the oxygen and pull those together. So here's an example of that, where I've done it for water. We just add the atomic masses up. So I took the hydrogen and found it, and it's 1.01 on the periodic table. And since it's water, there's 2 of them. I have to multiply that by 2. So the subscript becomes the number of times you have to multiply that atomic mass before you add up that with the oxygen. So oxygen, there's only 1. So 2 times 1.01 plus the 16 gives me a molar mass. Now we're talking about not an atom, but we're talking about still the same idea, the mass of 1 mole of water. It would be 18.02. So we're just adding up again the atomic masses so that we can talk about molar mass. So here's an example we'll do together real quick. I can say I have for lithium carbonate, I have 2 lithium atoms, and I have 1. The 3 is for the oxygen, so not for the carbon, but the subscript is for the oxygen. And I have therefore 3 of the oxygen. So we can take the weight. Lithium is 9.9419 on the periodic table. the weight for carbon, if you look on the periodic table, should be something near 12.01, and that for oxygen is about 16.00. So I can just take that 2 times the 9.9419. I'm just going to clear that. 2 times the 9.9419, and I get my 19.8838. And then I would add to that just straight up the 12.01, and I would add 16 times that 3, 48. So I'm going to add those together to get my molar mass of lithium carbonate. And I get, if I've done this right, 79.8938. I just want to mention during conversion problems that we don't consider that this is a limitation on the sig figs. Remember, information we're using from the periodic table in a conversion factor is not going to limit our number of sig figs. The measurement we start with in terms of in the lab is what we use. So this will be 79.8938 grams per mole of lithium carbonate. Now, for sake of time, I'm going to skip the next 2 slides. There's a story on multifocin that is a drug that's used to treat that brain-eating amoeba that you can have if you swim in really warm water. We'll come back to this slide in class, just looking at aspirin and how we determine its molar mass. And also, a little bit harder, this multifocin that's used to try to treat the folks that have had brain-eating amoeba, I guess they've been exposed to by swimming in warm water. It's a much larger molecular formula. But let's get to just 2 problems, I guess. We'll do example problem 2 and example problem 3, setting up the conversion train and then getting the numbers later. So remember, again, mapping, and I've added one more step in here because sometimes if we're dealing with atomic mass, we don't need this one, but if we're dealing with molar mass, I can have the grams to moles to number of CO2 particles, but I can also look at the number of atoms within that, we'll say a compound. You could say compound here if you wanted to. The number of atoms in that compound. So let's look at what they want here. They want grams, so we're shooting for grams. That's our goal. Where are they starting us from? Our N, 1.50 moles. Okay, so I'm right here. It said moles, and moles are right below grams of N2O, dinitrogen oxide. So it's really applying, just looking at this as a general guide, I'm really moving from here to here, 1 conversion car. So I'm really already in my mind's eye thinking all I really need is 1 conversion of a number they gave me, and that is 1.50 moles of N2O. All I need to do is 1 conversion. How do I know that? Because I know where I am. I'm in moles, and I know where I'm going. I'm just going to grams. This math will really help you if you lay it out on your paper before an assessment. So I know I have to have moles on the bottom, so I need to put 1 mole of N2O. And from the periodic table, 2 nitrogens and 1 oxygen pulled together is 44.013 grams of N2O. And that would give me what I want, my grams of N2O. And that would be a pretty straightforward calculation. 1.50 times 44.013. I mean, we'd keep the 3 sig figs. Pretty easy. So we'll have some harder ones in class. So here's our last one that we'll do on the video here. And again, you can have that plan and maybe just keep it simple: grams, moles, compounds, and atoms. What's the number of oxygen atoms in 2.45 moles of CO2? So now we're going from moles, not just a number of compounds. So we had kind of in our general, you may want to just think general. I have grams to moles to compound to number of atoms. We said particles here, but just thinking it's a molecule or a compound, something that's a collection of 2 or more atoms, and I may need to know the atoms within it. Well, here they do. They want to know the atoms. This is our goal. They want to know the number of atoms. And they're starting us off with something 2 steps above the moles. So we're here, and we're having to go through one conversion to get to compound, and then another conversion to get to atoms. So I've kind of laid it out more specifically. We have the number of moles of CO2. We're wanting to know the number of compounds on our way down, and then we're wanting to know the number of oxygen atoms. So what I'm going to do right away, just looking at my map, is say I have 2 conversions. It'll get me to the number of oxygen atoms. The number of oxygen atoms. And so to do that, the number they start us off with is 2.45 moles of CO2. And I know, because I've looked at my map, moles to compounds to atoms, I've got 2 conversion, 2 arrows. 1, 2. And so I'm going to start off with 1 mole. I just put those conversion cars up here to make it easy for us to reference. So I know 1 mole of CO2. I need to get to that Avogadro's number, 6.02 times 10 to the 23rd CO2s. Now remember, it's not 1 mole of CO2 and then 6.02 times 10 to the 23rd carbons. We're saying 1 mole of this is that number of CO2s. But I can get rid of this CO2. I can say for every 1 CO2 molecule, now that's going to have to be on the bottom, for every 1 CO2 molecule or compound would be more specific, it's different atoms. How many oxygen atoms do you have for every 1 CO2? I hope you're saying for every 1 CO2 molecule. So I had to flip this one. I have 2 oxygen atoms. So you'd have that right here, oxygen atoms. All right, that is how we set up our conversion train or dimensional analysis for these types of problems. Know where you are, where you're going, and therefore that'll expose the number of conversions you have. And then if you're doing a moles to number of CO2s or compounds, you have to use Avogadro's number. But at some point, we had to go ahead and go farther. We had to do that. So we had to go from CO2, there's 1 CO2, there's always going to be 2 oxygen atoms. We'll do more like this in class, but bring your notes annotated. Thanks. Bye-bye.